So, whoop. Hello. Our next talk is Dan Callahan, and he's going to be telling us about running Python apps on CoreOS.
Thank you. Mike? There we go. Thank you. So my name is Dan Callahan. I work in developer relations for Mozilla. You can find me on Twitter as @Callahad. 2 years ago, Docker got released, and ever since then, there's been this enormous amount of buzz and excitement about containerization on Linux. I'm not going to talk about Docker today. There's an entire talk on Docker tomorrow. You should go to it. What I want to talk about more is the impact that this interest in containerization is having on the rest of our backend server stack. So what does containerization change for the way we architect our host machines? And I'm going to look at this by examining a Linux distribution called CoreOS, which was released about 1.5 years ago. And it's designed from the ground up to run containers. Not that you need a special distro to run containers, but by looking at a distro that was designed kind of as a greenfield experiment in what an ideal host for containers would look like, we can see things today that I'm pretty sure will become best practices in 3 to 5 years. Or for those of you who are here from the Bay Area, containerization is scheduled to become a best practice on Monday. So be ready for that when you get back from PyCon. What are we actually trying to solve here? Why are people excited about containers? I don't do ops. Like, I have some weekend projects. I want to deploy them somewhere. I really want a platform that will stay updated automatically. I want that platform to stay updated in a way that won't break my apps by upgrading a dependency from out from under me. And I want a platform that will survive outages. So it would be really fantastic if I had a server and I pulled the plug on it, if I could trust that my applications will keep running somewhere else. Because if we have those 3 things, I can be lazy. And that's ultimately what I'm looking for, right? But to get there, we need something declarative. We need the ability to say, always keep 2 of these running and don't put them on the same machine. I could probably cobble something together that gets me most of the way there with enough cron jobs and shell scripts and external monitoring. But at a certain point, you start kind of collapsing under the weight of all this orchestration and this kind of Rube Goldberg machine of, oh, what's online, what's not offline, and then you don't want to touch your servers. And then you go months and months and months with this kind of faith-based DevOps that like, I trust that things will be okay. And then Heartbleed happens, and all of that technical debt comes crushing down. So the way that we get out of that morass, especially for kind of hobbyists like me, is moving to something declarative where we can define the state we want and trust that other systems are going to make that reality. And to do that, we need new technology. And we need that new technology, not brand new technology. This sort of stuff has been the norm inside Google, inside Amazon, Facebook for a while. But we need somebody to take Google's secret sauce and package it up in a way that we can run on our own servers. And in a sense, that's what CoreOS is doing. And so we need innovation in 4 key areas. 1, we need a better way to handle system updates. 2, we need a way to isolate our applications from the host environment. We need a way to cluster our servers together so that they can be reasoned about as a single logical unit. And we need a way to distribute tasks amongst the cluster. So in this talk, I'm going to look at how CoreOS solves each of those problems, how they move the state-of-the-art forward in each of those areas. For updates, we're going to look at FastPatch. For containers, for application isolation, we'll look at Docker and Rocket. For consensus and clustering, we'll look at a project called etcd. And for scheduling, the job of distributing tasks amongst the cluster, we'll look at Fleet and Kubernetes. And so we're going to look at each of these in turn and see what the theory is, what problem they're solving, and what that means for the way we design our architecture of servers and of our applications. And all of this is free and open source software. So one of the things that I really admire about CoreOS as a company is that they've contributed things like etcd and Fleet as truly open source projects. They have a commercial offering where they offer support and things like that, but you can stand this up today without having to accept proprietary software, without having to pay a dime. It's really fantastic. So let's start with system updates. CoreOS uses a system called FastPatch. What they're trying to do is decrease the gap between when a patch becomes available and when it becomes applied to your servers. Because staying up to date is key to good security, right? As soon as a vulnerability is known, as soon as a patch is made available, you're basically racing dozens of other people in the world to see if you can patch your servers before they can develop an automated exploit. So anything you can do to go from patch available to patch applied as quickly as possible, the better. And so the first thing CoreOS does is that they've adopted a browser-style update model. So you have update channels. You can say, I want the alpha, beta, or stable release of my operating system. And then in the background, updates get downloaded opportunistically. So a new version of CoreOS comes out, it gets downloaded. Next time you reboot, it gets applied. The other thing that CoreOS does is that they treat the entire system as a single unit for the purpose of updates. So what this looks like is when you boot into a CoreOS machine, you have 3 partitions. You have an A partition and a B partition, both of which hold the CoreOS system. And you have a data partition for your own stuff. These are mounted as read-only so that you can flip-flop between them. When an update becomes available, a daemon that has nice limits on how much bandwidth and how much CPU it can use will go download that update. It'll apply it to that partition. And these updates are effectively entire system images, right? Like you get a whole new ISO, basically, every time an update comes out. This is similar to the model that ChromeOS uses. So that update gets applied, and then the next time you reboot, you're running system B with that update, and then you have your data in the data partition. This has a couple of really nice properties. One is that for whatever reason, if that update's bad, you can just reboot again, and you're back into A, into a known good state, right? So you've got updates that are recoverable, you can roll back on. The other nice property of the system is that the updates are atomic. And what that means is that instead of going package by package, like with apt-get or yum, where if a power outage happened halfway through your update, you might be left in an inconsistent state. With CoreOS, either the whole update got applied or nothing got applied, which is really, really important when you're dealing with automatic reboots of your servers, right? Like you want to know that you're not going to have an adverse event leave you completely broken. So we've got a server, it's running our app, the server's running CoreOS, and you're probably thinking to yourself, wait a second, Dan, my server's rebooting on its own, how do I keep my app online? Naive answer is, let's just add another server, right? We have 2 servers, we should be okay, except what's causing the server to reboot? An update becomes available, the server notices, it downloads it. Both those servers are going to see the update at the same time. So now both your servers are rebooting at the same time. How do you keep your app online? Right, we can just add increasingly more servers until, like, asymptotically, we probably won't have them all off at the same time. A better solution might be to introduce consensus, introduce clustering. And we're going to do that with a tool called etcd. It's bundled with CoreOS. etcd is a really basic key value store, and it gives us a place, if we stand up a 3rd server running etcd, to store metadata about the cluster. And so we've got 3 servers, 1 for etcd, 2 for our app. And on top of this central place to store configuration, all that, CoreOS builds a tool called locksmith. So whenever a server wants to reboot to update itself, it has to acquire a lock from etcd. And then when it comes back up after the update, it releases the lock. So this means you can govern the rate at which updates roll out across your cluster by limiting the number of locks that are available. It also means that if an update comes out that's bad, that your hardware won't boot from, a server will grab a lock, attempt to reboot, it won't come back up, so it will never release that lock, which means you can't have a cascading failure due to a bad update. Let's look at what that looks like. So I've got 2 CoreOS virtual machines, and I've got locksmith, and I can look at status, and I see that I have 1 lock available out of a maximum of 1, so I can go ahead and say lock. And if I look at the status again, we can see that this machine has acquired a lock, and it's now cleared to reboot. If I try to lock on this other machine or acquire a lock over here, I get an error because there aren't any more locks available. The server has to release the lock first. And so all this is doing is it's just writing and reading from a key in etcd. So let's look at etcd control and say ls recursive. And so we have this kind of leaf node here that if we say etcd control get, we can see it's just a little JSON document. 0 semaphores available out of a max of 1. The machine with this ID is currently holding it. And so with etcd, we can actually come over here and say watch forever, that key, and now we'll be notified when it changes. So if I unlock this server, we can see the updated document. If I relock, so really nice way to get notified of changes to your cluster's configuration, right? And so when a lock's available, the server can then go get one, reboot, and we'd all be in a really good place. Does this solve our problem of our servers rebooting? Yes? No. Guess what's also running CoreOS? The etcd server. My etcd server is rebooting on its own. How do I keep my app online? Right, add another server. So you may be sensing a theme, right? We have a server, and then we want more. And you just keep getting more. So the nice thing about etcd is that we have this single point of failure. To get away from that, we need to distribute it. And etcd is designed to be distributed. It's actually an implementation of a system described in the Chubby paper by Google. The main difference is that etcd uses a consensus algorithm called Raft instead of Paxos. Raft is just better decomposed. It's easier to implement. It has identical fault tolerance and performance characteristics. In English, that means that you can take this system and for development and testing, it's fine. You can do this. You can run it all on the same thing. But if you're actually going to production and you want to keep this stuff online for real, you can set up a cluster of etcd nodes. We got 4 more servers. Generally, you want to keep the etcd cluster a static size, like 3 to 5 should be fine. And the nice thing about this is that because of that consensus algorithm, as long as a majority of those nodes are online and can see each other, the cluster will keep working. So with 5 nodes, 2 of them can fail, and the cluster will work as if nothing happened. And this sort of an architecture can support tens, hundreds, thousands of worker servers. So this is what you'd want to go to production with if you had, say, a bunch of EC2 spot instances that you're spinning up to run workloads and then going away. You'd have those on one side, and you'd have a more persistent set of etcd nodes to help coordinate the cluster. Everyone follow? Clusters, yeah, distributed systems. Everything breaks in interesting ways. For these demos, I'm going to be setting up a 3-node cluster using a local virtual machine. I'm running etcd and my apps on the same nodes. You could theoretically go to production with this, but you really don't want to because you can't, in this sort of a system, easily drop and add other worker nodes, right? It's much better to keep those separate. But for demonstration, we're good to go. The nice thing about etcd is that while it's bundled with CoreOS, it's an independently useful project. So etcd has been adopted by Google's Kubernetes scheduler. It's been adopted by Pivotal's Cloud Foundry, by Mailgun's Vulkan proxy, and seeing actual collaboration and reuse. Cool technology, right? But we haven't actually talked about how we're going to run our apps on this thing. We've just talked about how we're going to stop all the servers from rebooting at the same time, which is an important problem. But that doesn't actually make us any money or let us show off our side project or anything like that. The reason that CoreOS is able to do full system style updates is that they make the operating system extremely bare bones. So the whole ISO is 140 megabytes, which means there's no room for Python, Perl, Ruby, or JavaScript. There's no package manager, there's no compiler. Remember, the base system is mounted read-only, so you can't even muck with things under user bin. So what do? How do you run anything? You use containers. So containers at a very high level are somewhere between a really lightweight virtual machine or a really heavyweight chroot. The idea is that instead of a virtual machine where you're coming to a host and saying, here is an entire software-based definition of a whole computer that I want you to emulate, with a container, you're just saying, here's a file system. Run that program in it, and keep it isolated from other things. Thanks. And you're trusting the host system to provide the isolation, to provide the kernel. And this is kind of cool, because you still get the accounting and the management style of a virtual machine, but you get much better density, much better performance, because every container on that host is sharing the same kernel. It's much more like launching a local process than emulating and booting a whole machine. And this has a lot of benefits. Docker kind of popularized this in the Linux world, but this idea has been around for a long time. FreeBSD had a system called Jails back in 1998, which implements basically the same thing. We're only seeing this buzz now because Linux, in the part of the mainline kernel, only started adding a feature called C groups to give similar isolation in the last 6, 7 years. And it's only been 2 years since Docker showed up and said, hey, wait a second, we have this capability. We should wrap it up in a high-level interface that makes it usable and define a serialization format so that we can actually build an image here and share it somewhere else. CoreOS ships 2 container runtimes. You have Docker and one of their own design called Rocket. Rocket's designed to be a lot more minimal. They're trying to use Rocket to narrow in on a specification, an interoperable specification for serializing containers. Docker is much more interested in, like, we have a working implementation that's all open source. Let's build from there. It gets dramatic and political. They both do the same thing effectively. So how does this actually work in practice? So let's come over here. Wow, that was a cool sound. That wasn't me, was it? All right, so I'm shelled into one of my core machines, and I've got a really basic pyramid application. So there's my hello world. Don't read it, it's ugly. It's from the tutorial. I don't know quite all that much about pyramid, though it's looking nice. I've got my requirements.txt, which says pyramid equals 154. And then I've got a Docker file that's really basic. It says from Python 343 on build, and command is python3 hello.py. So what Docker lets you do is it lets you create this hierarchy of system images. So if we look at Docker images tree, less. So we can see that there is this Debian image up at the top, and then as a descendant from it is this Python on build image, and then there's my app at the bottom that I built beforehand in case the network went down. And so what this on build image does is it basically emulates a Heroku build pack, and there are ones of these for a bunch of languages maintained by Docker themselves. And so when I try to build this, you'll see that it says, all right, I'm going to copy the requirements.txt into the container. I'm going to run pip install on it. I'm going to copy all of the source code into user source app, and the image is built. And so now we can say docker run, and we'll map port 80 to port 8080 in the container, and we're running the container my app. Nope. There we go. And so now if I come back over here, bam, hello world. I've got an app running in a container. Hello PyCon. So like there's real software running in a container right now. And that's not super impressive, even though you clap, so you're very nice. Instead of running that command, let's run bash. And exit. Oh, look how fast I can start and stop containers. Can't do that with a VM. Every time I invoked that command, bash was created inside a file system snapshot from this container, had isolation from other things in the process, or on the operating system, just like you would expect with a virtual machine, but way lighter weight. And so if I look around in here, there's my app. This looks like a Debian install. I've got apt-get. I've got an etc Debian version. So inside the container, I look like I'm in a Debian system, even though I'm being run on a CoreOS system. And this is a huge benefit for containers. You can develop a container locally that has a user land from Debian or from Arch or from Gentoo, and then you can go and deploy that on Ubuntu or Fedora or Red Hat, and it doesn't matter. As long as you're using modern Linux and you're hosting on modern Linux, it'll just run, which is really fantastic. But we haven't actually talked about, like, I'm going and manually running things. That doesn't scale. We want to get to that nice declarative place where I can say, keep 2 of these running, but not on the same machine. And that requires something that's akin to a cluster-level init system. If we were just dealing with a single server, we have things like supervisord, we have things like upstart, sysvinit, but we're not dealing with a single system anymore. So there are two schedulers that work really well with CoreOS. It gets bundled with one called Fleet that's pretty basic. And there's one called Kubernetes that's part of, it's open source, it's by Google, they have dozens of engineers on it. Kubernetes is super complex. Like if you've got millions of servers and you're trying to eke out every last % of efficiency, you want Kubernetes. If you're a real person, Fleet will be fine. The nice thing is both of these are independent components. You can swap them out as you need it. CoreOS's commercial offering, Tectonic, uses Kubernetes, but again, meh. And both of these are built on etcd. So another pattern, like it's not necessarily scheduling or any other thing that gives us high availability. All this comes down to is having consensus on the network, having that one place, etcd, where we can agree on what the state of all the machines are. So Fleet's simple. Fleet's a clustered interface for systemd. If you are a Linux nerd, you have heard things about systemd and you probably don't like it. Unfortunately, every major distribution kind of seems to like it. And so what systemd does is it lets you write unit files that look like this, where you say like, here's my app, it requires Docker. Before it starts, go try to kill any other versions of it and remove them. When it starts, go and run this thing. Just like you saw me run on the command line, right? Docker run, map the port, whatever, and use Docker stop to kill it. Everything up here is a normal systemd unit file. What Fleet adds is this little xFleet section at the bottom, which can have things like conflicts my app, at star.service. This is the thing that tells Fleet not to put two of these on the same machine. And you have other constraints available to you. You can say, put this on a specific machine running another container, or put it on a specific machine by ID, or based on metadata. You can say, make this global, run it on every machine that's available. So we have all that. Let's look at what it actually looks like in practice. So I've got this service file. It's just what you saw before. And I'm going to inspect my Fleet cluster. So let's list machines. So I've got 3 servers. We'll list units. There's nothing running on them right now. So let's take this unit file and say Fleet control submit my app service. The at symbol is kind of a systemd thing. It's a template. So it says, hey, replace like this I with the number of the thing you're running. So if we start 1, it'll be 1. If we start another one, that one will be 2. And so what submit does is it takes that unit file and stores it in the etcd cluster. So let's say etcd control ls recursive coreos.com. And so let's see, that looks like it. So if we say etcd control get that, bam, there's our unit file. It's got a hash, which points to this. And there it is. You also see Fleet keeping track of the various machines that are available. But we're not actually running this yet. We've just made it available to the cluster. So I can list unit files, and we can see that it's there, but it's not active. Let's boot one of these up. There we go. Let's start another one. So this launched on the machine ending in .101. The second one's going to launch on, oh, wait for it, 1 or 2. That's coincidence. It could have ended up on 3. But if we look at Fleet control, list machines, we can see those machines. List units. We can see those apps running on those various machines. And we can use normal systemd commands. So like we can say journal, or status rather. Let's do status. My app at 1. And so we can see that RM in the kill failed because there wasn't a pre-existing image, but the main process is active and running. And here's the last bit of output from running that. So I can see that for anything running, even though I'm on core 1, I can look at that on 2. And I can actually say fleet control SSH and jump over to the box that's running my task very easily without having to kind of dereference it. So that's how we go from a unit file to having 2 things running. I promised you high availability, so let's go kill one of these. So let's say, oh, this is way small, make that big. Project speaking, PyCon, CoreOS 6. So we'll shell into Core02. No, whoops. Vagrant SSH Core02. There we go. All right, so we're in this machine that's running my app 2, right? So let's shut down H now. Oh, sudo shut down H. And so, bam. It's gone, and it's up on 3. So we can reboot that machine, and if you were doing this with a normal scheduler, when this machine comes back up, it's going to try to restart that file. Not so because, in this case, because Fleet's the thing that's controlling what happens. It's like, wait, I already have filled this. I'm running on 2 servers already. 102 doesn't need to restart it. So when this comes back up, we can say list machines. We've got the 3 machines again, but that's still just running on machine 1 and 3. Kind of cool, right? At this point, like you've still got to figure out, like, all right, I've got my stuff. It can survive. Let's go kill another. It can survive a machine getting the plug pulled on it. But that means you have to design your apps differently. If a machine can go away, if a container can be killed on a machine and then show up on a different machine, you have to minimize state, because you're not going to have that same hard drive available to you. Heroku wrote a really nice document called the 12-Factor App Design Principles. Really worth reading that. It talks about how they've come to build apps that work well on the Heroku platform, which has many of the similar design constraints. But this doesn't actually solve things that actually need state, like databases and load balancers, right? Because I'm over here, I've got this thing running on 101 and 103. There it is on 101. There it is on 103. But it was on 102, and that's totally dead now, right? So you still need to have something in front of this doing load balancing. And that's okay. There's not a great story for statefulness in this sort of an architecture yet. But you don't have to run your whole environment on CoreOS to reap the benefits of running a lot of worker processes on it. In some cases, if you're on like Amazon EC2, you can outsource this. Like you can just pay money to start up an ELB or like an RDS or something. But you could also, for weekend projects, fine. Go bind your database, say like only run this on machine ID X, and it reboots, no big deal, right? Like it'll be out for a couple minutes every couple of weeks. You're still going to be okay, and it's still it does get you to a better place than you were beforehand for the stateful parts. But it does get you to a much better place for the parts that aren't necessarily stateful, right? If you have ideas for making this better, like things like Postgres, right? Postgres is not cluster aware. So if you need Postgres, like you need to kind of babysit it still. Great room for innovation. But at the end of this, like we've done it, right? Like we have a platform that's self-updating, that's self-organizing, that's self-healing. And we did it by using an operating system that automatically updates, that uses atomic whole system updates. We put our applications into portable, isolated containers. Oops. Ah, no, don't redirect to oh man, there we go. Web technology, man. So we also set up multiple containers, or multiple servers in a coordinated cluster using etcd. And we used a scheduler Fleet to distribute jobs across the machines in our cluster. So now it's your turn to play with this, right? Like I've shown you that it's possible. I've shown you what designs change. Like things have to be able to die and come back up on a different host. Your turn to play with it. CoreOS is supported on a ton of platforms. I did everything on a local virtual machine, trio virtual machines running Vagrant. You can also do this on Azure, EC2, Google Compute Engine, Rackspace. All of these have official CoreOS images. And DigitalOcean, as of last September, also supports CoreOS natively. A friend of mine actually just started working at DigitalOcean. She told me to tell people to use the code SammyLovesPyCon to get a $40 credit if you're a new customer. So you can go and spin up 3 $5 a month VMs and play with this for 2.5 months using that code. Feel free to retweet it, give it out to people. Super great. But I've been talking to you for a while, so let's take some questions. You can find my slides online there. Check out DigitalOcean, use that code. Like, free stuff, right? Mike is in the back. Thank you so much.
Hello. Can you hear me?
Okay. Yeah, there we go.
All right, great talk, Dan. I wonder if you could say a little bit about what the experience is like running CoreOS and Docker on a Mac development environment.
On a what development environment?
On a Mac development environment. Does it suck?
It kind of sucks. So the one of the premises with containerization, right, is that you're going to share your kernel between all of your containers. And obviously, if I'm using a Mac and I'm trying to run things on Linux, like that's not going to work. So you still need a virtualization layer. Not ideal. I mean, it's totally fine for testing. There's a Vagrant CoreOS recipe that makes it dead simple to spin up 3 of these things, play with them. But you're still booting a VM to then go run other VMs because you can't do this natively on your desktop. If you're working on containers and you're on Linux, you're way ahead of the game. But you know, it is what it is. We're deploying to Linux. You got to deal with it somewhere.
And you just give it an enormous amount of RAM.
Yeah, pardon?
You just give the Vagrant container an enormous amount of RAM and walk away.
Yeah, basically. I mean, CoreOS doesn't take a lot of RAM. I mean, the whole thing's super minimal. It boots really quick. But yeah, you have to be running the containers on Linux. There are obviously, like, Microsoft just announced a containerization solution for Windows earlier this week. But containers aren't portable across operating systems. They're portable again across distributions. So like a container that has a user land from Red Hat will run on a host using Ubuntu or Gentoo. But you can't take like that container like you could with a VM and then go run it on Windows.
Hey, Dan, great talk. Quick question. If you have a service that depends on having something on disk persistently, and you want to be able to start this service on any sort of arbitrary node, how are you going to create a file system which, say, is shared across those instances that this service will have access to?
There's not an answer for that baked in. I mean, if you're using EC2, you can go and use like elastic block storage. There's now an NFS client, elastic file service or something. Mm-hmm. So you'd want to just do a normal kind of network file share or a network block mount and manage that outside of this.
Right. Cool, thanks.
Yeah.
Great talk. Quickly for the guy in the blue Firefox t-shirt, there's boot to Docker. That kind of gets you like a very slimmed down VM that you can run on OS X, which is pretty good if you want to play around with the Docker side of things, just FYI. Boot to Docker.
Yeah, boot to Docker is great.
So my question is around Fleet versus Kubernetes.
Mm-hmm.
So I know there's a lot of work that you guys are doing with Kubernetes. I'm kind of confused on what the kind of future path is, because there seems like Kubernetes is doing a lot of things that Fleet is doing. So is there a difference? Are you guys moving towards Kubernetes, or what's the kind of, am I wrong about that?
So one point of clarification, like I'm not those guys. I work for Mozilla. I'm just kind of a hobbyist in this space. Okay. But I did talk to Kelsey Hightower, who works for CoreOS, before I gave this talk, and the sense I got from him was that Fleet is an excellent basic scheduler. And if you need Kubernetes, you know it. Like when you start running into things where if you get 5% better, better allocation of your resources, you save millions of dollars in the power bill. Like that's when you move to Kubernetes. But Fleet itself is still a great primitive. So you could use Fleet to bootstrap the Kubernetes clients on the other workers and things like that. It's clear that Kubernetes has a lot of momentum. Google has tens of engineers on it full time. Yeah. But it seems really targeted at much, much larger scale deployments.
Okay, so you kind of see Fleet, not you, but just the kind of Fleet and Kubernetes kind of existing side by side, I guess.
Oh, absolutely.
Okay.
This is just a brief follow-up on an earlier question. Have you experimented with Amazon's Elastic Block Store as a means of persistence with a database server like Postgres or something else? And do you think that's sort of ready for production yet, or is that just it might work if you try it sort of thing?
It's more of I mean, it should work within the constraints of EBS. But the things I'm doing, I mean, like I'm working on hobby projects. And this stuff, everything I showed you will scale to hundreds or thousands of servers. I'm caring more about like 3 because I don't want to deal with that one email once a month where it's like, hey, there's a hardware problem on your server. We rebooted, and I'm like, oh man, my stuff was offline. So I'm trying to fix that at a very low level, and I find it interesting that this sort of technology actually does scale down to that pretty well. Okay. But I'm putting all my stateful stuff in like RDS on Amazon.
Okay, thanks.
The stack you have been presenting is really interesting, and I would like to know how this is fitting other configuration management tools such as Salt and Puppet, where some company might have invested in manifest or states, and how do you see the transition? Because like the transition between something which is declarative and where you have all your configuration targeting something to such a volatile thing.
Right, so it seems like the CoreOS platform itself, I mean, your system's mounted as read-only. You can't really change the configuration. I mean, you can obviously add things to /etc and that, but it in a certain way obviates the need for tools like Chef, Puppet, SaltStack, Ansible, because you're not trying to configure these machines. You still need to be able to build a container, but the tools that exist for that, like the Docker files that say, you know, go download this, run this, do that, kind of take care of that. And then once you're done, that single container is portable. You can serialize it, you can SCP it from one host to another, and it just picks up and runs without having to have like the long-lived configuration management or the configuration convergence things that you usually get with those sorts of tools. So it might get rid of them, which is kind of terrible, but getting rid of stuff is also kind of good.
So if you have like 1,000 application servers and you know, then 5 etcd nodes doesn't seem like a big deal. But if your scale is 3 app servers and you need a node of 3 to 5 etcd things, that doesn't seem to make sense. So if you're in production but with a low number, is that how they use it there?
Yeah, this totally makes sense. You get all the redundancy of like, this is a production-ready deployment just with 3 nodes. The problem there is that if one of those machines dies, like if you're using EC2 spot instances or something, you have to take a lot of care to inform all the other etcd nodes that this one is no longer something they should be looking for. Because if something else shows up, then all of a sudden you've got a really weird system in the part that does consensus, right? Because it's like, wait, I have 4 things. I thought I had 3 things. And it gets weird. But if you're just standing up like a couple of long-running VMs of a fixed number, that configuration works great. Traditionally, you don't want to turn on all that many etcd nodes. Performance starts degrading after about 9. I think in the Google Chubby paper, they had 5 machines handling tens of thousands of concurrent clients. So you know, something like that really does scale enormously. Something like that's fine if you're used to a traditional long-running VM. Yeah. There's time for one more.
So you'd made a comment, and I've heard it a number of times, that this automatically updated and saved you from a number of security problems. But it didn't.
Yes, I think I know where you're going, and this is great. Thank you.
Because your user land is where libSSL lived. And none of your libSSLs on your cluster got updated when everything rebooted.
Spot on. So this would help you with things like kernel level vulnerabilities, but you still have to maintain your user land. And so what you want to do is end up making sure that you're rebuilding your Docker images regularly, redeploying them and things like that once things come out. The nice thing that this gets you away from is having to manage both the host system and the application system with a lot of care, right? Like Red Hat will sell you a 10-year subscription so you don't have to update, and that's kind of scary. This lets you worry about, here's my application, I can update that on its own and not worry about what else it will affect.
And that's all the time we have for questions. Thank you so much, Dan.
Thank you.